All right, guys, let's start our class today. Good morning, welcome back. So this week we look at ROP, return-oriented programming. And actually more specific, this is return to libc. So just like we look at libc's a way that like we look at ways that we can take advantage of libc when we exploit the Stack Overflow, especially when the defense are turned on. So we talk about all different kinds of defense, right? So if you look at the video, you saw SLR, you saw stack canary, you saw NX, right? Like non-executable stack, right? And then now you realize that actually in this case, you will not be able to really exploit with a shellcode because the shellcode is going to be stored on stack, right? And then if you turn on like NX, then you will not be able to execute it at all. And also, if you turn on SLR, you will not be able to tell the address of the shellcode very, like very, in a very straightforward way, because every time that you run the program, your stack address will be changed. You cannot like look at previous run and I found the location of the shellcode and then reuse that as the address, then put that into the overwritten as the overwritten returned value, right? So you don't know what you want to write. Like if you remember last week, we talked about shellcode, we talked about exploits. It's about two parts. One is where that we want to jump to, right? And then the second is what value that we want to jump to, right? So in that case, that we will not be able to know what the value that we want to jump to. So in that case, then ASLR disables us from doing that. However, the ROP attack just smartly bypasses those by assigning a return address go to somewhere that is still executable, such as somewhere in libc or somewhere in your original binary, and then you use that as the so-called gadget, like it's part of your purpose of our execution, but not the full purpose. And then you just chain those gadgets together in order to achieve your purpose, such as to call a system call and then call it execve so that you can call /bin/h. So if you look at the videos, you know, like on the high level, how it works, okay? So today we are going to, let me just jump here real quick, actually. Today we're going to have the lab that we're going to, work on this together. So the first thing that we're gonna have is a lab that has, I'm gonna ask you guys to spend some time to do a shellcode attack. So for that attack, so far, the stack is still executable, but because last week we haven't tried shellcode exploit. So I'm gonna ask you guys to try shellcode exploit by yourself. And then later on, we're gonna work together on a ROP, like a ROP attack, okay? Before we go to the lab, I wanna first ask if there is any question in terms of, ROP, in terms of defense that we talk about during the video. And then now is a perfect time for you to ask. In fact, on Tuesday's class, we have many people ask me about like ROP, how it works. I explain it again, go through the lecture, go through the slides again to talk about how ROP works. So if you have any questions about how it works, this is the perfect time for you to bring it up. Yes. Yeah. Yes. But the stack is not executable, so how will it like? Yes. Right, that's a very good point. So the question is that since the stack is not executable, why is that you can still put some address on there and then so that you can execute? So the difference is the following. So the stack itself is not executable. It means that if you put an instruction there, which is what you exactly do for shellcode, right? So in your shellcode, you have instruction by instruction, such as move EAX. I'm just gonna have a random one, like move EX1, right? That's an instruction. So the instruction itself is stored on stack, and that is not executable. However, think about it in this way. On your stack, you also store the return address, right? Like even though there's no buffer overflow, you store every time you call a function, the return address is saved on the stack, right? And then in that case, it's the address of the instruction is saved on the stack, not the instruction itself that is saved on the stack. So that by the time that your function returns, the computer does is that it reads the saved return address, right? So it only reads the stack. It reads that address, and then it executes the instructions that are stored in that particular address. But then that address is not on the stack. I mean, when I say not on the stack, it's not belong to the part of the stack. The address itself goes to another place that stores the instruction, and then that place is executable. And in fact, let me just show you this picture real quick. I think this will answer your question. Okay, yeah, so I am showing you this picture. So this is the memory, like how the memory looks like by the time that you run the program, you execute the program. And then you see that there are many lines here, right? Like those are many small segments that are on the memory. And you see that those are not totally consecutive. Like this is a small segment, right? And then followed by some small segment. And then it will just directly jump from 555Y, those segments, to another 7FFF, right? So like those segments, they're separated from each other. And in fact, if you look at this specific column, this is the permission of those small segments. So some of the segments are readable, executable, but not writable, right? And then some of the segments, they're not really executable, right? So this is what happens for a stack and also the other part of the code. So if your program, like, of course, your program has code, has instructions, and then those instructions, they're stored in a different segment from stack. So that's why if you look at the instruction, those addresses are very different from the address of the stack. And then you only make stack not executable. So that's why your shell code, those instructions are not going to be executable. However, sorry, 1 second. What is that? Oh, yeah, it's no problem. Sorry. Yep, you can enable a caption if you want. Okay, so that only means that the stack is no longer executable. However, if you point your stack to somewhere like from your code or from libc, it's still gonna be executable. And that explains why you can still use ROP to execute the instructions, because those instructions originally they're already executable. Does it make sense?
Just to confirm, so are we using the address of the stack to point to some executable location?
Yes, exactly. The address of the, yes, the content of stack points to the address of my executable location. Okay. All right. And then besides that, is there any question in terms of how ROP works? Like, can you write a ROP chain by yourself? Yes.
So what I got from the advice is that every instruction or a couple instructions that want to go together,
Yeah,
followed by a return instruction, right?
exactly.
How difficult does that make to find like instructions to go together?
Yeah, that's a good question. So the question is, how hard is it to find instructions or find, you know, a gadget that has return, has read at the end, right? So that's a very good question. So it depends. Like if you have a huge library, for example, libc, if you have libc with you, then it's relatively easy. And also, by the way, you don't have to really read the code to search and search it by yourself. There's existing tools that assist you about that. So all you need to do, just run that tool. Actually, I think I mentioned here, right? Like these two tools, we're gonna use it today. One is RobGadget and the other RoPM. Like use these tools, they're gonna load the binary, like load the libraries or the program that you write, and then they're gonna find a gadget for you. So if you have a huge library that are attached with your process, then it's gonna be very easy. And also, I wanna mention it's not only just the libc, because if you see here, all you want to do is to find some library or some binaries that there know is executable. So you can also just find the gadgets from your own program. And also you can find the gadget from, the loader, the linker, like by the time that you run the program. So they're all instant memory that's available for you to use like as a gadget. So it's not really hard, but also, I mean, there are challenges, not for our assignment, just like sometimes there are challenges that are particularly trim the binary, make it very, very small and hard to find raw gadget. But like in general, it's easy. Sure. All right. So I have questions here. I want to double check with you guys. Like when I talk about this Rob chain, like here, the way that we link them all together, do you think that it's necessary for me to explain to you how this works? Like why that we can chain that in this way so that we can make Rx is equal to hex 3b and so on? Okay, sure. I'm happy to explain this to you. All right. So I'm going to explain this to everyone. And if you have questions, interrupt me at any time. Okay, cool. All right. So let's start from here. So suppose that we have a buffer flow, so we can just overwrite the whole stuff. Okay. And then the goal for us is to be able to, make a system call. And this system call is system call execv. So although I'm writing this in this way, it doesn't mean that I'm calling a function with an address. What I mean is that this is a system call, okay? And then in this system call, we're gonna pass 3 arguments there, okay? The first argument tells the system call that, hey, I want you to execute this specific program. And then the second and third is the argument and environment variable. We just pulled it out because we don't need to pass anything there. Okay. All right. And then in order to achieve this, okay, what we need to do is that we need to make RAX equal to hex 3b. This is part of the system call because the system call comes with a code. Like all the operating systems, they have system calls, but system calls has to have a specific code they're associated to specify which type of system call that you're calling. For example, if you have a system call with Rx equal to hex F, it means that you're gonna make a system call called sig return, okay? Or if you have, or if I remember correctly, if you have Rx equal to 0, it means that you're gonna read. That's the system call, okay? So that's in here, like hex 3b is associated with execve, okay? And then the next is the arguments. According to calling convention of x86 64, RDI has to point to the string. And then RSI and RDI has to be equal to 0. Yeah. Yeah, good question. Is 3B for all the OS or is Linux only? Yeah, for Linux operating system, hex 3B means that you make a call execv. Okay, cool. Yeah, good question. All right. So far so good. So like this is the purpose. The left-hand side value is our goal. Okay, and we want to somehow chain them together so that we can achieve the left-hand side goal. Okay, cool. All right. So now let's continue. Let's see how we're gonna make that. So remember that this place is the place that we originally it stores the returned RIP, right? Like right after saved RBP is the place that stored the original saved RIP, right? Good. Okay, so remember that. And then going to this picture, it goes to here, right? So this means that if we manage to overflow the buffer, then by the time that the vulnerable function returns, the computer will look at the value here, right? And then make the RIP's value equal to this value, and then jump to that particular address to continue to execute, right? If you remember previously, in maybe last week or 2 weeks before, we have the slides that says return is equivalent to 2 instructions. One is to pop RIP, means that given the current stack, I'm gonna pop that value out and give that to RIP, right? And then the next is to jump RIP. Means that, okay, now I change the RIP's value. I'm gonna jump to that particular place and start to execute, right? So similarly here, let's say that we have this particular, value, we override, and this value is the instruction, which means that this is the address, right? That points to these 2 instructions, okay? So that means that by the time that the vulnerable function returns, this value will goes to RIP, and then we will start to execute here, right? We'll start to execute this instruction. So far, so good? All clear? Okay, cool. And also keeping in mind, where is RSP at this point? Because we do a pop, right? So again, pop RIP. So RSP goes to here, right? So by the time that we're about to execute this instruction, we have RSP RSP, pointing to this particular location. And now we're going to do the next instruction, which is pop RAX, right? Okay, so we want to move some value to RX. Remember, the goal for us is to make RAX is equal to hex 3B, right? So then in this case, then we make the followed stack value, like this stack location stores the value of hex 3B, so that now if we pop, this value will be given to REX. Make sense? So it's like here is very straightforward. We know that currently RSP is here. We're about to execute pop. We do a pop. Okay, now we do a pop. RSP will move again because this value got popped out, right? And then this value goes to REX. So now it's the moment that we finish executing pop REX, and REX is already equal to hex 3B. All good? Great. And now, according to the instruction, we need to return again, right? Because the instruction tells us we're going to return. So now this is where RSP is pointing to. And then according to return, which is equal to this, right? So we pop the stack again, give that value to RIP, right? And that's why we managed to chain the gadget together, because here, this particular location, it stores the instruction of the next gadget, right? Which will be pop RDI in a return. So in that case, by the time of the return, when we finish this instruction, RIP's value will be equal to the address that points to pop RDI and return that gadget, right? And also we will jump to that location, okay? In this way, we finish like a transition from one gadget to another. And then similarly, we're gonna do this again, until we manage to make all the value as what we expected. Does it make sense? Okay, cool. Okay, So sometimes when you search gadget, you're not gonna get the perfect gadget. For example, here we have pop RX right after return. Sometimes the gadget is not perfect. There might be some junk in the middle. For example, you have pop RX, but also you have maybe move, say EBX or move RBX equal to 1. But we don't care because it's fine that we contaminate other registers as long as we don't use them, we don't need them by the time that we run the system call. So that's perfectly fine. However, sometimes you will figure out that some of the gadgets, they will overwrite the register that you already assigned the value. And you want to be flexible. So you want to be moving the gadget flexible enough so that by the time that the last gadget was done, was finished, you got everything correct. So you can move the order. And in fact, in today's ROB, you will see that I think it's because of RDX. The RDX gadget has a register move, has assigned like value reassignment to register RAX. And then because of that, we don't want to do pop RX return first because we know that if we do that first and then do RDX assignment, RX value will be overwritten again. So we want to swap the order. So it's just like a pretty normal like operation. Like ROB, it's something that is very flexible. Like you don't really want to follow like a specific order, a specific pattern. It's more like you're writing a code by yourself. But then the only difference is that instead of writing the code, you look at a dictionary or look at, a book and then try to find some sentences over there and chain them together to achieve your program, to get, your code. And that, I don't know if that makes sense to everyone. Good? I see many of you are nodding your head. I suppose that's a good. All right. Yes.
That means we are pointing to some other place in our stack where these instructions are.
No, you're still pointing this stack. The stack doesn't change. So by the time that you pop, you are operating on the stack. So it's always the same stack. And that's why ROB works, because in that case, you can put the variable, like put the value that you want like RX become here, so that by the time that you pop, this value, which you already control, can be assigned to RX. So it's always one stack.
And user means that we are referring to some other location, right?
Wouldn't be end, there's no end, return.
And pop that.
Oh, and sorry. Yes. And means that you're pointing to some other location. And in this case, it's the location that stores this instruction. And in our case, it's libc. So basically, yes, I mean, that's a very good question here. Sorry, I misheard your question before. Right, so this place, like the end of this means that you point to somewhere in libc that contains this specific instruction. Yes.
And then we have
Yes.
that's going to be a problem.
Exactly. Yes.
What if there is a deadlock, which means that when I'm doing pop RAX, it is assigning the value of RDX to 1. But when I'm doing pop RDX, it is moving something else with RAX.
That means that your ROB chain has some problem. You need to write the ROB chain correctly so that you will not have this problem. Like just you said, like if you miss hex 3B here, right? That means that by the time it pop RX, it will actually consider pop RDI as the value that you assign. Sorry, yeah. Yes.
You told that it is flexible, that we can change the order of the instruction.
Yes, it is possible. You can change the order of those gadgets. That's exactly what I'm saying. Sometimes you have to change the order.
Yeah, so you gave an example that when we do move RDX 0,
Yeah.
It is changing the value in RAX.
Right.
And so it can also be like, there can also be a case where when we do pop RAX, it's changing the value in RDX.
Yes.
So now if both are changing each other's value,
Then you say you're screwed. You have to find another law there.
Ah.
Yes. Good question. So the question is, I'm gonna repeat it here again because I don't think that Zoom people can hear the original question clearly. So the question is that, because I just mentioned there will be the case that, like, for example, when we do pop RDX, we overwrite the value of RX. What if that the gadget that we found for pop RX will also overwrite the value of RDX? Then that means that there's a depth loop there. How are we gonna do? That means that you have to find another gadget that will bypass this problem. Okay,
So in
Yes.
this case, when we are executing move RDX, so it will override the value of RX.
yes.
So then how will our instruction? Because the value has been overridden.
Sorry, can you say that again?
I'm just like,
Mhm.
so if we do move RDX, then it will basically override the value of RX,
Right,
which is 0x3.
right,
Is our instruction,
right.
right? So then how will the instruction execute? Because the value has been overridden.
Yes, because the value was override, so you don't want a RAX value to be overwritten to someone else, right? So what you're gonna do is that you're gonna have the move RDX, that gadget execute first,
In this case.
right? In this case, because in that case, then you're gonna leave this assignment of RX in the end so that your RX or the overwritten will be overwritten again by itself to the right value.
So in this case, the correct order would be like first you move RDX and then you do the rest.
Exactly, exactly. I mean, or you can do RDI for, as long as move RDX is earlier than pop RAX, you're good. All right, cool, awesome. Yes,
So, in the stack difference, there was like the stack canary thing. So the stack canary is protecting the part before the, RIP, but it's not protecting this part, right?
Yes.
So we can override this part.
exactly, exactly.
Regarding the stack canary, so
Yeah.
like why does it have the last value is 0? Like you had explained that part. Like,
Yeah. Right, so this is a good question. Why that the canary is designed in a way that the last byte is 0? This is mostly because, you know, well, usually when we read like a string, or say let's do start copy, like those kind of a string manipulation, it will always stop when you see the end of string, which is 0, 0. So this is a very smart design for stack canary in the sense that they make the last byte to be 0, 0, so that if someone want to overflow, they want to keep the stack canary value same as what it was, right? But then they have to make this byte equal to like 0, 0. And then in many cases, if you make a string with the end of, or with a character 0, 0 in the middle, then they will consider your string finishes. So in that case, you will not be able to really overwrite the rest of the canary. And then it's not the case for our stuff. And this is because we use gets. Like it's a very dangerous read in, and we just read as long as what it wants. But if you use another thing such as like scanf, right? It will read until it see a 0, 0 there. So that means that if you have a scanf in this case, then you will not be able to really overflow the buffer if you have stack canary there, right? Of course, if you don't have stack canary there, you can still overflow the buffer because there's no 0, 0 character protection. There will not be a 0, 0 that will cut your string. Okay, make sense? Cool. All right. Now we finish all the questions. It's already 11. Good. Okay, let's do our in-class lab. So it's the same address, different ports. This time it's 5555. And I want you to download, those files. You can also interact with the server, but it's going to be important for you to download the files, especially the last two ones. And I can tell you why. And that is because if you want to run the binary locally, you will need these two libraries that is the same directory of the stack. of your service binary. Okay, so put them under the same directory and then run them. Because I have kind of like modified the binary so that it will only use the libraries that is in the current directory for them, just in case that you have different libcs and different libc will have different Rob Gadget address. So this is like this three are something that you really need. And then the first one, which is the source code, is just to help you understand what's going on for the program. Okay. All right. So please do not rebuild your binary. If you're not using glibc 2.31, or if you just don't know what I'm talking about right now. Because if you rebuild, you will not have the self-modification that I have for the current stack. And then you will use your own system's libc to run with your program. But then in that case, all the gadgets that you find will be wrong because the address is not the same as the same version that I'm using right now. So make sure that you don't rebuild the binary, okay? Unless like you're using Ubuntu 2004 and also having the glibc 2.31. Okay. All right. And also, so far, let's just focus on shellcode right now. So I'm gonna give you guys some time to see if you can use your own shellcode to do a shellcode exploit. I'm gonna give you probably 15 minutes. So now it's 11:02. Let's start with like say 11:15, I would say. Okay, so let's start 11:15 that we are gonna work on the Rob Gadget Rob attack together. All right.
Yes, as long activating,
Do I have SLR?
activating the search. Situation.
I don't.
Okay.
I don't. Yeah, I'm pretty sure I don't.
Okay.
Yeah.
That would affect perhaps the.
For sure, yes. Good question. Do you have ASLR enabled? No. I don't have ASLR enabled. That's why you can still use shellcode because you will be able to locate the address of the shellcode. But then if you were asking me, do I have like NX enabled or do I have Pi enabled? I would say I won't tell you because that's something that you can figure it out by yourself. You can use check sec to figure it out.
We say ampersand bin message.
Mhm.
So it means that we write bin message somewhere else and just point that address here or.
Yeah, you don't have to, that's, first of all, it's a very good question. And the second, this string, you don't have to put that on stack. There are many places that has this string. You can find this string from libc.
Okay.
Yeah.
Using Rock for the start of also vulnerability of Rock part of vulnerability. There should be there so that you should Rock file also. Is it some no it's non-executable vulnerability? So we are using for the Rock part.
So I didn't quite get what you said.
I was asking what we are using to explore this type of when we
Are you trying to use ROP or shellcode?
Rock.
ROP, okay, yeah.
So I was just asking like what part should we enable or disable in the start also availability for MVC Rock to exploit it?
You don't need to enable anything and you don't have the permission to enable the accessibility. like the executability or executable. I mean, when I talk about those are just defense that are already turned on or turned off, like from the environment. And then
Okay.
in this challenge, in this case, it's, as I just said, the ASLR is disabled.
Yeah,
So you can use
but if
LLR,
it's
yeah.
enabled, then we cannot use that.
No, if it is enabled, even though the ASLR, if it's enabled, you can still use ROB. And that's the point of why we're talking about ROB, because ROB is like powerful. It
Mm.
can bypass all the three defenses that we talk about, like
Okay.
NX. Well, it doesn't really, it can't really bypass Stacanary, but like SLR
Mm.
and NX, this is something that can be
So
passed
it
by
can
ROB.
bypass SLR, it can bypass boundary, it can also bypass non-executable code.
Right, right, because Rob is giving the instruction, not, sorry, the instruction address, not the instruction on the stack.
Oh, okay.
Yeah.
So with just, okay, so we're just going to the RFP entrance,
Mhm.
and we are giving the shellcode on the RFP. entrance.
And for that, you have to have,
Okay,
uh,
Rob Gantt.
no, for that shellcode thing,
Mm.
you don't need Rob. I mean, that itself is another way to attack, which is to use shellcode.
Okay.
And for that, your stack has to be executable.
Mm.
Right, but then if the stack is not executable,
Mm.
then you must use Rob.
Okay.
Yeah,
Thank
sure. All right, guys, last minute, I'm gonna replace the slides with terminals. So if you still need any information from here, make sure that you captured it right now. And I'm gonna replace this with my terminal in 5-10 seconds. Very fast. All right. Okay, guys, let's work on this together. First of all, I already see some of you managed to log in yourself. Good job. If you haven't, that's totally fine. That's why we're here, gonna work together. So don't worry about that. Okay, so let's do this all together. First of all, can anyone tell me what's wrong with this service? What's the vulnerability? Where does this vulnerability occur? Can you say louder? I can't hear it, sorry. Line number 45? 45, yes, exactly, the gets, exactly, yes. So that is the location, right? So this is the place that the program takes an arbitrary long string. However, ID has only 50 bytes. So we can overflow ID and then we can, you know, overwrite the return address and then do whatever we want. Good. And then I'm not gonna tell you how to do that on shellcode. I suppose that you already tried that by yourself. I saw some discussion online. Sometimes you have questions about like shellcode. Some of the shellcode doesn't work, right? You can change other shellcode. I haven't looked into why, because the code that I shared with you from the video, it works for me. I'm not sure why it doesn't work for you guys. But yeah, if you have questions about that, you're more than welcome to actually come to my office hour and I will help you debug. Actually, I'm curious about why that happens. So yeah, but then any case, today we're gonna talk about wrap. So the first thing first, similar as what we did before, let's create a template first, okay? So we can do Pong template. Oh, also, actually, you know, as I just mentioned before, I told everyone that ASLR is disabled, and that's why you can use shell code. But you don't know, like for example, if NS is enabled or not, if those things, other security check already enabled or not. So I'm going to do check sec followed by stack. I have a different name, but it's the same binary as what you have. So it will tell you what's going on here, right? So it tells you there's no stack canary, there's no NX. And also it has Pi enabled already. Okay. So those are something that we're interested in. Those that we know that, okay, we don't have to worry about stack canary. That's great. And then we can do, you know, execute, but now we're going to try rob anyway. So it doesn't really matter if NX is enabled or not. Okay, cool. All right. So now let's work on this together. Again, let's create a template. Right. So what I just learned yesterday is that you can also specify the host, like put the API address here and also the port when you generate a template. So like in that case, you can generate a template that has this, I'm gonna put a random stuff here because I just can't really remember our IP. And then it will generate a template that has remote option. So demo Thursday.py. Okay, so it is here. This is similar to what we have from last time, right? So this, you should be pretty familiar with the template. All right, so now we have the template and now we want to start to interact with the service, right? So I'm pretty sure that you're already very familiar with this, but I have to do this again anyway, because I have a plain template that I want to start with. So I want to read those information, right? The value of the base pointers, so which is the RBP's value, the buffer's address, right, where your ID will be stored, and also it gives you an extra information, which is the base address of libc. You may wonder why would I want this? How I'm going to use it? And I'm going to show you later. But so far, let's just parse all those information to your code. All right. So it should be pretty straightforward. You have our old receive 2 and then your BP is equal to hold on, receive line. Keep ends false. So when I pass this keep ends option, I'm telling it, hey, I want to receive a line, but please just toss away the last byte, which is the new line byte. I don't care about that character. Okay. All right. So now we have the base pointer, right? And then the next is the buffer, right? Okay. So I am going to be stored and have this equal to, I'm gonna just call it buff. Okay. All right. What's more? The libc base address. Okay. I'm gonna just call it base. All right. Awesome. So now we have these three values, right? And then now let's just write the skeleton first, the skeleton of the exploit. Okay, the exploit has to be equal to some random padding that I'm put over here. In my video, I just do like A times the length, but here I'm gonna do cyclic. And the length will be, so it is BP minus buff and then +8, right? The reason why we put +8 here is because the return address is always stored at RBP +8. Well, actually, maybe this is better for you guys to understand. So this first part is the address of return address. Save the return address. And then the second part is your current buffer. Yes. Okay, yeah. And also, by the way, I highly encourage you to follow me, like type as what I'm typing right now, right here. You don't have to do a screenshot. You don't have to take a picture of it. Later on, I will share this code with you guys, okay? So I want to just concentrate on the knowledge itself without worrying about, I can't write the code, okay? All right. Is this found good enough? Good, cool. All right, I'm gonna continue. So now the next is, of course, the ROP chain that we care, right? Now it's the time that we start to build a ROP chain. I'm gonna put a ROP function there because I'm gonna write it as a function. All right, so far so good. I'm gonna write the ROP chain now. If you remember, the goal for us is to call execve, right? Oop. And then it is gonna be binsh. And then there's null, right? And then in order to do that, we need to make RAX is equal to hex3b. RDI is equal to an address that points to this string. Okay. And then RSI is equal to 0. Also, RDX is equal to 0. And the reason why they're this specific register is because of the X664 calling convention, but you don't have to worry about right now. It's not going to be very important for the attack. All you need to know is that, okay, in order to make this call work, I need to make those registers equal to those values. Okay. All right. So now we need to find them. Let's find them from libc. Okay. So I'm going to open another panel, increase the font. So we're going to start with trying to use Ropium because Ropium is a tool that can find a gadget for you directly. So I'm going to do load. I can't remember those commands for sure. So I'll just use help. So if you feel concerned, like why Tiffany can remember all the commands, but I can't, do I have to remember them all? The answer is always no. So don't worry about that. The reason why I can remember it now is just because before this class, I practiced it for many times. I won't remember this a week ago. So don't worry about that. All right, so now I'm gonna load the library. Do you remember the library that I give it to you? You should download it. And this is time they're gonna pass it to Ropium to have it find the gadget for you, okay? Let me take a look at the name again. It's libc. So it's this name on my end, but it should be libc.so.6 on your end, okay? You load it. And that's just a warning. We always just ignore warning. So don't worry about that. Just wait. Okay. So now it's finished. We're going to do find. So we need to find, for example, we want to find a gadget that makes RAX is equal to hex 3b. All right. It tells me that, hey, this is the location that you will have a pop RX return gadget. Fantastic. This is exactly that we want, right? And also it tells you that don't forget that you have to have hex 3b next to the stack, right? Because that means that once you do pop RX, this value will be popped and it will be assigned to RX. Okay, good, makes sense? All right, so now let's write this. Pop RAX is equal to these two addresses, right? We need to put them together. So I'm gonna write it in this way, hex 4A, 54F, and then hex 3B. This is the gadget. Okay, cool. Okay, and then let's do next. RDI, but then in this case, we have to find, you know, this string. And then unfortunately for Ropium, it's very hard for them to like specify, find a string in my library. But fortunately, we have other tools, which is called RobGadget. So I'm going to use RobGadget. Oh, I think I typed something wrong. I went to R. Here we go. Actually, let me just turn this off. I don't want to make my screen too crowded. Let's do RobGadget. I always can't remember RobGadget's command. So I'm gonna just help myself. Binary. And then that is libc dot 2.3. This is the library. And then I want to find the string with /bin/h. So it's gonna be string. I think we need to give it double quote. Here we go. All right. So now we have a location that has this string particularly, right? Good. Then let's go back to Ropium. So what I want to do is to make RDI is equal to hex 1B7588, which is the address that are in libc, right? Okay. It tells you you can use this RobGadget followed by this specific value. Good. So now I have pop RDI. Right. Oh, I think there's a typo. If you have any questions, feel free to ask me right now. Okay. And then the next for us is to find gadgets that do the other stuff, right? RSI. So it's going to be RSI is equal to 0. And also RDX is equal to 0. And okay, for RSI to equal to 0, they have also a very clean and tidy pop return gadget. So we just put that in. That is pop RSI X 27529 and then 0. Okay. And then the last one, right, which is actually it's XOR EDX. So that is hex 14271. However, you see that what it does is that it will do XOR EDX EDX, which is to make RDX equal to 0. But then the next is that it moves some random value to EAX, which is not something that we want, right? So that's why by the time that we chain those together, we want to swap the order. So I'm gonna swap it right now. So we want to make pop RX the last, so that after we have the value of EDX or RDX in this case, we then rewrite the value of RX again. Okay, make sense? Okay, and then rest is easy. All we need to do is chain them together. But of course, we have to make those things, you know, packed little endian 64 bits, right? Okay, so we can do, I'm gonna write this in a something that you may not be very familiar with, but don't worry about that. Pop RDI plus pop RSI, pop XOR RDX plus pop RX. Okay. All right. So I'm just using this Python's map. It means that I want to make every element in this list and then map those elements to a function called P64 and then return a list. Okay. And then later on, then I want to make all those together because I don't want the chain to be a list. I want it to be a byte string. So I'm going to do this join. All right. Okay. Let me just return chain. All right. Okay. Cool. I'm not sure if this is going to work or not, but let's try this together. So we can do temp it together, and this is local. Oh, this is because it's going to. Something is not really working because now I'm just trying to type something. It doesn't really respond me. Okay. Okay, good. The reason is that it doesn't see this will be stored. That's interesting. It shouldn't have a problem there. Let's work on this together. I think I might typo something. Is it the same? I think it is the same. Base pointer.
We don't want to do slash and in the IO before we plan.
You don't need that because I'm using receive and to. So it will.
In the first time, so that was in the second time. Yeah, here.
Which one?
Yeah, here we don't have to do, we slash and in the first time.
You mean here?
No, in the receive line function.
In the receive. It shouldn't be a problem because in the receive line, we receive this entire line, right? You know what? Okay, let me. Let me do interactive. So yes, I will also make the problem that I don't know what's going wrong.
Professor?
Yes.
Yeah, in the program, you are trying for receive until will be stored 2 times, whereas in the stack patched thing, the will be stored string is not
occurring 2 times. Can you check that?
Which one is 2 times and which one is not 2 times? You
In
said
the
the stack
program,
that you have, yeah?
yeah, in the program we are reading like will be stored 2 times, whereas in the stack patch it's not occurring 2 times. So maybe we have to check for some other string, like for example address of libc.
Yes. You said that you don't have address of libc in your code or,
Template, yes. In the can you check the template?
okay, let me check that. Is that true that you guys don't have a address of libc in your code? You don't have that? Or you do have that? You don't have that? Give me a second, I'm checking from my end. Yeah, you do have the address of libc, right? So it should be good. You should have a identical. 1 second. Yeah, you should have the same.
Yeah, I was talking about the template which you are editing right now.
Sorry, I don't understand.
Professor, in the template.py, can you scroll down? I think he's saying will be stored is called twice, like you're receiving until.
Oh, interesting. Sorry. Yeah, that's right. Okay, and now I see your
Yeah,
point.
yeah.
Yeah, I'm sorry about that. I didn't notice you mean the code that I'm writing, sorry. Yes, I'm gonna change that. I don't know why I'm having this twice. Oh, it's because the base, I see. Right. Thank you. So it should be address of libc. Then we should be good. Let's try that again. Thank you. Thank you for pointing out my bug. Yep, and now it's working. Good. So now what we need to do is we want to do ro.receive and to as you write ID, right? Okay. And then we want to send the exploit. Okay. Let's try this. Cool. Okay. So you see that we are sending something, but also we get EOF, which is not supposed to happen. And in fact, we found that there is 6app, right? There is something wrong with this program. Okay, don't worry. Let's debug it together. Okay. So if you're going back to the program, you see that as many of you see that the error happens after this gets, right? Okay, so let's just set a breakpoint here at line 52. So it's like right before we return a function. Let's see what it looks like. And by the way, my laptop is in a low battery. I wonder if you have a charger for me. Like yes, the USB-C, not really the magnet. Yeah. Do you have like any C charger? Thank you. I forgot to burn it again. Thank you very much. Yeah, exactly. Cool. Okay. Now let's come back. So let's debug this together. turn on DDB. Make a breakpoint. Let's break at line 52. That's where we said, like right before the function returns, right? Okay, now let's continue. So now it's right before. Let's see what it looked like in the info frame. So we have save RIP equal to this address, right? And then that address is what we found. Here we go. What we found from our ROP gadget, if you remember, right? This is hex 26B72. That is what we found for pop RDI. And then going back. So it is the same. It sounds like things are good, right? Okay, but then let's take a look at this particular location. Let's see if it has the address. It has the instruction that we want. Okay, so let's do X and this address. And then we want to output in the format of instruction. There seems there's a problem. It says that it cannot access memory at this particular address. So the reason for that is because if you look at the memory map, so for libc, the way that it works is that it will load into your process at a base address. And then those instructions or those addresses that you found from ROPM are just the offset of the libc. Means that starting from the beginning of the libc, going to that many bytes, you will start to hit that particular instruction. But then by the time that your program runs, by the time that it executes libc, it doesn't recognize libc from address 0, but instead it will look at this, the memory, the process's memory, find the base address of libc, and then have that plus the offset that you find for the instruction. So what you need to do is that instead of putting the offset or putting the ROPMs offset there, you also want to find the base address of libc, which in this case, we already give you. And if it's correct, let's compare this address with what the program outputs to you. So I'm trying to figure out which one that I'm running. Not this. I have too many tags here. Okay, this is the one that we're running right now. Yeah. Right. So in this case, I was hoping that it can output something, but it doesn't because I didn't let it output. Okay, let me output something for you guys, because in that case, you should be able to see the same address shown from what we have parsed from the output. Let me do this again. Let me use the script to output. Okay. Which is base. Okay. I'm hoping that this will output something to us. Okay, going back here. So remember, this is the address of the base, right? And then hopefully it output. Okay, good. So it outputs this address. So remember, this is 34A0000, right? And then going back to what we have here, it is this base address. Okay. And then in fact, if we have this plus the offset that we have, for example, we know that the one of the offset which is for pop RDI is this, right? Let's just add these two together. All right. So let's do this plus this. Okay. It has something, and that's exactly pop RDI. Okay. Okay, so then now let's finish this. I know that we're running out of time, but we're very close to the end. Going back to the code, then our exploit should have all the base times this, right? And then this is also base because this is where we found the string. And then also here is the base, but not this 0 because this is the absolute value they want to pass to RSI, right? And base, and then base, okay? And then we need to pass the base back here. And then going back to the original ROP, we want to pass the base there. All right, so in that case, we will be able to have an entire ROP. Cool. I hope this works. If not, I will let you know what's going on later on, but finger crossed that this works. This is my last effort. Oh yeah, this is because. Good, it still doesn't work for some reason. I have no idea why, but I will debug this and let you guys know. But I think it's very close. I will let you know why this doesn't work, but also I will share this code with you right away after this class and you can debug it for me. If you found it earlier than me, good job. Okay, awesome. Thank you. Yes,
Right, XOR for one of the instruction.
right,
Yeah, that's what I
XOR.
bought, the third one.
Oh, that's because for that one,
Yes.
the gadgets that I found is using XOR.
Oh, okay.
Yeah, so I'm just like use that way to name the variable, right?
Can you please explain again, like, why did we use XOR?